Okay, in this video I want to do some more enzyme problems and enzyme concepts, and I want to talk about the kinetics a little bit. Just the most important concepts. I mean, the textbooks, whatever textbook you have, whether you have Lineager's, Principles of Biochemistry, or one of the other textbooks, they're going to go into painful detail when it comes to enzyme kinetics. I'm just going to try and cover like the very basic intuitive understanding that you need to start working with these things. If you're interested in the real nitty-gritty details, then the textbook should provide that information for you. So let's get right into it. So enzymes exhibit saturation kinetics. As the relative concentration of substrate increases, the rate of the reaction increases, but to a lesser and lesser degree until a maximum rate known as Vmax is reached. So basically what I'm saying by that is we can continue adding more and more substrate to a solution. And as we add more substrate to the solution, as the concentration increases, the rate of the reaction is going to increase. This makes sense. I mean, this is just basic, chemistry here. You add more substrate, the reaction rate is going to increase initially. But what happens is, as time goes on, more and more substrate is added. Individual substrate molecules must wait for the free enzyme. So what happens is there becomes like a backup. There's not enough enzyme molecules to keep up with all of the substrate. Hence, it's saturated. And the Vmax is then proportional to the enzyme concentration. And to see that visually, I actually have the graph here. And we can kind of see the curve here. Again, it's pretty much a hyperbolic curve similar to myoglobin that we looked at before. And if we look down here, this is the concentration of substrate, and here's the Vmax. And as we increase the amount of substrate, or the concentration of substrate, we see this graph, shoots up really sharply, and it shoots up really, really fast at the beginning here. But then it levels as it approaches Vmax. So that's what they're saying, when they're saying that it exhibits this sort of saturation kinetics, and that the rate increases initially, but to a lesser and lesser degree as Vmax is approached. So the next thing I want to talk about is what's known as the turnover number. You might also see this listed as K-cat, so it might say something like K-cat. And when you're dealing with this, basically the turnover number is the number of substrate molecules one enzyme active site can convert to product in a given unit of time when the enzyme solution is saturated with substrate. So when the enzyme solution is saturated with substrate, this is basically a measure of how many molecules of substrate can be converted to product by a single enzyme, or by a single active site. And like I said, that's known as the K-cat, and that can be calculated, K-cat, you can use some mathematics here obviously, as Vmax over the total concentration of enzyme. So that's sometimes called ET or ETOT. I'll call it ET. So the K-cat is the Vmax over the total concentration of enzyme. So that's basically a way you could calculate it if you were given some numbers. Related to Vmax is also what's known as the Michaelis Constant, and that's Km. So we have this other constant known as Km. And the Km is the substrate concentration at which the reaction rate is equal to 1/2 Vmax. So if we look at the graph again that I have here, we can see it's listed. The Km's listed right here. Here's the Km, so it's the Michaelis constant. And it's just equal to 1/2 Vmax. Okay? And unlike the Vmax, the Km does not vary. This is actually why the Km is important, or how the Km can be used. And unlike Vmax, the Km does not vary with when enzyme concentration is changed. Therefore, the Km is a good indicator of an enzyme's affinity for substrate. So basically, we talked about affinity for oxygen when we were talking about hemoglobin and myoglobin, and that's why I said that hemoglobin and myoglobin are good ways to start thinking about enzymes, because they exhibit a lot of the same properties. Not all the same properties, but a lot of the same properties. And what we're talking about here with the Km is we're talking about the enzyme affinity. How tightly does this bind? And like we saw with myoglobin, the oxygen binded really tight to the oxygen bind it really tight to myoglobin, even at a very low concentration. So what we're seeing here is a very similar thing. We're seeing that the substrate is binding to the active site of the enzyme really, really tightly, even at fairly low concentration of substrate. And then as you add more substrate, it increases. And the Km again, once again, is just equal to 1/2 Vmax. So, moving on, I figured I would bring this up. I don't want to talk in great detail about the what's known as a Lineweaver-Burk plot, or this is called a linear plot. This is the same. It's a representation of the same information I just talked about. It's the exact same thing as this graph here. It's an exact representation of this graph here, but it's modeled in the form of a straight line. And you might be saying, well, what the hell does this mean? Why is this helpful? Well, this is actually extremely helpful, because if we go back to basic algebra here, we have a line, and we remember that the equation of a line is, y equals mx plus b. And if we just look at this line here, and we look at what these things are and what these representations are, just like we did in algebra, we want to know about the x-intercept and y-intercept. If we look right here at the y-intercept here, which is, this is 1 over v and 1 over the substrate concentration for the y-axis, but if we look here, for the x-axis rather, for the y-intercept here, it's 1 over v max. So this is like a really, really convenient way to get the Vmax. It's a really convenient way to model this too, because if I were to have a bunch of different numbers here, and I plug these into an Excel program, I could actually get this equation, y equals mx plus b, and then all I'd have to do is set x equal to 0 and get the y-intercept, and then I'd set y equal to 0 and solve for x and get the x-intercept. And if I had the y-intercept, like I just said, I have 1 over Vmax, I would just have to take the reciprocal, and I would get the Vmax. So it's really, really convenient way of modeling this information. And likewise, the x-intercept over here is equal to the negative 1 over the Km. So this is, again, really, really simple, because the x-intercept then just becomes, the reciprocal of 1 over Km. So I could just take the reciprocal of that, and I get, and I'll be able to get the Km. So remember, the Km is 1/2 Vmax. So from this information right here, really, really easily, and this is something you might be asked to do on an exam, or you might be asked to make an Excel spreadsheet or something like that with a bunch of different points on it. You can not only make graphs of these things here, but you can also easily find the Km and the Vmax. So that's really what this is beneficial for. And there's an equation for the line here. 1 over V is equal to Km over the Vmax concentration of substrate plus 1 over Vmax. So like I said, I just wanted to kind of give you the idea of what you needed to basically know about it, and the ways in which I was asked to use it was sort of in this form, where I was given like the equation of a line, or I had to find the equation of a line, and then I had to use that to calculate the Km and the Vmax. So there's a lot of good stuff you can do with it, and it's important to at least understand intuitively. Now I just want to go over some more information about enzymes here, just some basic concepts here. Temperature and pH also affect enzymatic reactions, which makes perfect sense, because recall that enzymes are usually globular proteins, and globular proteins are usually held together by weak interactions, weak intermolecular forces such as hydrogen bonds, ionic interactions, and as you increase the pH or as you decrease the pH, you can affect, and of course the temperature, heat is energy, and heat is one of the main ways to disrupt any intermolecular interaction, especially hydrogen bonds. This enzyme is going to start to denature. So that makes, it makes perfect sense that changing the pH drastically, or even minor changes in pH rather, or changes in temperature can affect enzyme reactions. And at first, it's kind of interesting, because the temperature actually increases the rate of reaction, because we know, one of the classic ways in your organic chemistry lab or your general chemistry lab to get a reaction to work is to just add heat to it. So it's kind of interesting that at first with these enzymes, as temperature increases, the reaction rate goes up. But the problem is, at some point, the enzyme denatures and the reaction rate drops off drastically, or drops off altogether, rather. For enzymes in the body, the optimal For the enzymes in the body, the optimal rate is I shouldn't have said rate. This should say For enzymes in the body, the optimal temperature is often 37 degrees Celsius. So that's just regular, temperature. You might be asked to do it at 37 degrees Celsius and make calculations at 37 degrees Celsius. Then again, you may be given something like 25 degrees Celsius, and don't make that mistake of just using 37 as a standard number. Sometimes the problems give you other temperatures that you can make calculations at. Anyway, enzymes also function with specific pH within specific pH ranges. The optimal pH value depends on the enzyme, so that makes sense because it's going to depend on what type of interactions are going on within the globular protein, what type of an active site we have, and such. And there's two kind of really simple examples that everybody's probably heard of, and that's pepsin, which is active in the stomach, prefers a pH below 2. It makes perfect sense, and the stomach pH is very low. While trypsin in the small intestine works best at a pH of 6 or 7. So you can see here that there's a difference based on where these enzymes are located and what their function is. In order to reach optimal activity, many enzymes require a non-protein component called a cofactor. And cofactors can be coenzymes or metal ions. So that's about as far as you have to go with cofactors and coenzymes. Some professors might cover them really in depth, but for the most part, it's just getting an intuitive understanding of what they do. And coenzymes are divided into two types. There's co-substrates and prosthetic groups, which are attached by covalent bonds. It's kind of important to know because a lot of, say, allosteric effectors are not attached by covalent bonds, but rather they're attached by, weak intermolecular forces like hydrogen bonds. Both are types of organic molecules. Co-substrates reversibly bind to a specific enzyme and transfer some chemical group to another substrate. So they reversibly bind to an enzyme and transfer some chemical group to another substrate. The co-substrate is then reverted back to the original form by another enzymatic reaction. The reversal to the original form is what distinguishes co-substrates from a substrate. So that's what makes it different. Remember, the substrate binds, some sort of reaction happens, and it releases products, depending on what reaction the enzyme catalyzes. In this case, you have this co-substrate that binds here, and it reversibly binds, but what ends up happening is it's regenerated at the end. The co-substrate eventually is reversed back to its original form. And that's what distinguishes the co-substrate from the substrate. And coenzymes are often vitamins or vitamin derivatives. Vitamins are essential and cannot be produced by the body. Heme is an example of a prosthetic group. Remember from hemoglobin, or you might remember that from cytochromes, which are involved in the electron transport chain. They're involved in the movement of electrons between the different respiratory complexes. So that's another place where you'll find heme. And metal ions are a second type of cofactor. Metal ions can act alone or within a prosthetic group or with a prosthetic group. Typical metal ions that act as cofactors are iron, copper, manganese, magnesium, calcium, and zinc. And that's just simple. You can have things like, again, with the cytochromes, you can go from like Fe2 and then it can become oxidized to Fe3. With hemoglobin, the heme group stays in the Fe2 state, though. And the last little bit here that I have is an enzyme without its cofactor is known as an Avo enzyme and is completely non-functional. So an enzyme without its cofactor is known as an Avo enzyme and completely non-functional, and an enzyme with its cofactor is called a halo enzyme.